All right, so guys, let's take a quick look at this next slide. Has anybody ever seen this hexagon before?
Yes.
Yes, you have? No, you haven't. You immediately went the other way with that. All right, so second period, there were 5 or 6 people that were saying, yeah, that looks kind of familiar, but the majority were saying no. So again, this goes by a couple of different names. By the way, you have a URL printed on your notes. I know that obviously you can't, it's not clickable, but again, if you wanted to see a little bit more, this is it. I don't know. I like this approach to it because it really tries to simplify things. Like again, this mathisfun.com website, they focus on a lot of like more elementary type things. They do get into some higher level stuff like with this here and now, but they explain it in a way that's very easy to understand. So again, if you want any more on this, I would highly encourage you to just go search for it. All right. But this hexagon, I've seen it go by a few different names. I most commonly refer to, and what you'll hear me refer to it as the trig hexagon. I've also seen it referred to as a magic hexagon. But really what this does, this helps you to remember your trig functions. There are, again, it's a relatively simple looking hexagon, but there are a ridiculous number of things that this helps you to see. Okay, so the way that you are going to build it on your own, you'll have to remember that you're going to start with tangent. So what is tangent again? What over what?
X over Y.
Or actually, y over x. Sine over cosine? Tangent's equal to sine over cosine. So as we work our way around, tangent is equal to sine over cosine. Or if we go straight across, what else is tangent? Is that 1 over cotangent? Okay, or sine is 1 over cosecant, or secant's 1 over cosine. So you might notice that you have a 1 in the middle, and reciprocal pairs are across from each other. Okay, they're across the hexagon from each other. Okay, so like we said, tangent's equal to sine over cosine. Can we go the other way? Is cotangent equal to cosine over sine? Yes. Now you would never use it, but tangent's also equal to secant over cosecant. Or you could say secant is equal to tangent over sine. All of those, like I said, you'd never use them. They're not identities. But in a pinch, like, yeah, you could make some sense out of that. Okay? Like I said, a lot of the stuff that you can do with this trig hexagon is, frankly, it's just like, oh, that's cool, and then you move on. But there are a few things that are going to be very, very helpful. The main one that I want to focus on is that if we have this hexagon, do we agree that that is, with the diagonals, that's cut into 6 triangles? Yeah. 3 of them are pointing downward. So we're going to focus on the downward pointing triangles. Sine squared plus cosine squared equals 1. Is that one of our identities? Yep. All right, let's go to the next one, pointing down. This is saying that tangent squared plus 1 equals secant squared. And then our last downward pointing, we could say that 1 plus cotangent squared is equal to cosecant squared. So I wish I had the reason as to why, but a lot of students struggle. Quite frankly, a lot of students struggle with memorizing these 3 equations. Maybe you would consider memorization a strength of yours and you're not worried about this at all, but you will most definitely need to know these 3 identity equations. You're going to need to know those like as soon as possible, okay? For whatever reason, like I was saying, though, a lot of students struggle to remember these 3, but they can easily remember this hexagon. So if you can easily remember this hexagon and you understand how we're doing the notation from top left, top right, bottom in terms of the triangle, that tells you the whole story, great. If that's what you need to get started. All right? So moving forward here, are we understanding the whole cofunction identity thing? I think so. A little bit. Okay, if not, we'll circle back to it later. All right, so guys, even, odd. Remember, we touched on this in chapter 4. Even functions. What makes a function even is that if you plug in a value or its opposite, you get the exact same thing back. So we say that, that cosine and secant are even functions. Okay? Same example we used in chapter 4. Let's look at 30 degrees. What's cosine of 30 degrees? Root 3 over 2? Okay, what about negative 30 degrees? What's cosine of negative 30 degrees? We still get root 3 over 2. So we're saying that it doesn't matter if you plug in a positive angle or its opposite. You're going to get the same cosine value back. Okay? Same would go for secant. But on the flip side, if we're looking at the sine, still 30 degrees, the sine is going to be 1/2. Negative 30 degrees, the answer There, we're going to get negative 1/2. So there, it's odd because if I put opposite values in, I get opposite outcomes. All right? Just like we have with all of our other types of functions. Again, we always utilize the quadratic, f of x equals x squared. That was kind of like our baseline. That's an even function. The cubic, that's our odd function. 2 cubed is 8. Negative 2 cubed is negative 8. Squaring, though, 2 squared is 4. Negative 2 squared, still 4. Right? So that's the difference. So again, our trig functions are going to still work at those or within those patterns. Essentially, what's going to happen? Like I said, all this identity stuff, it's just shortcuts. That's all that it is. If we have an odd trig function, so like, again, all three of these examples you see, we've got sine, we've got cosecant, tangent. We don't have a cotangent, but that would fit in here as well. All of the odd ones. If we're going to find an odd function of a negative angle, essentially what we could do is just bring the negative out front. Now, would we go one step further and actually evaluate? So what we're saying is, we probably know off the top of our head what's the sine of 45 degrees. What's the sine of 45 degrees?
Square root of 2 over 2.
Heart attack here. Yes, we know that the sine of 45 degrees is going to be root 2 over 2. We brought the negative out front, so we made the whole thing negative. Okay? Same thing, cosecant of pi over 6. All right, well, we know, again, just bringing that negative out front, pi over 6, I know what that coordinate is. Root 3 over 2 comma 1/2. Cosecant is going to be the reciprocal of sine. What's the reciprocal of 1/2? Just 2. Oh, but I brought the negative out front, so that's going to be a negative 2. Okay, same thing here. I think we're getting the idea. We're saying that if we have an odd function with a negative angle, just bring the negative out front. Okay, how's that going to be different down here with the evens? Does it matter if I'm finding the cosine of negative 45 or 45? So again, same is going to go here with the secant of negative 840. It's the same as secant of 840. So if you have an even function, the negative sign is obsolete. It doesn't really, it's a non-factor at that point. Okay? Now, once again, I do want to stress, I'm going to move on for time purposes, but we wouldn't leave it as the negative tangent of 60 degrees. Like, we would actually evaluate that, right? Okay? All right, so guys, we want to get through at least 2, but we'll see how this goes. So what we're looking at here, we've got sine x cosine squared x minus sine x. Now, I'll be the first to admit here, and we're going to talk about this in much greater detail tomorrow. 5.1 is harder than 5.2. 5.1 is harder than 5.2 because we don't have a target here. Tomorrow, in 5.2, it's going to say this is equal to something like that. Now our job is to make the left side look like the right side. Okay? It's easier when you know where you're going. Here, we don't know where we're going. Okay? So from here, we're going to have a lot of tricks that we learn along the way. One of the main tricks is that if you have an addition or a subtraction problem, doesn't look like it, looks way more complicated, but isn't that a binomial? We have this thing minus that thing over there. So if we have an addition or subtraction problem, can I factor something out?
Yeah.
What can we factor out in this problem?
X.
No.
You can.
Doesn't work like that. This is sine x, that's cosine squared x, that's sine x.
You can factor out negative.
Can I factor out a sine x?
No, wait, there's a cosine.
Then we're multiplying. So guys, what this is really like is this would be like 3x squared minus 3. That's what this is like. But instead of 3, we have sine x. Okay? Okay, so yes, we can factor out a sine x. I really didn't think that was going to be the part that threw us off. Okay? So if I were to divide this whole thing by sine x, what are we left with? Cosine squared x. If I were to divide this part by sine x, what are we left with? We're left with 1. Negative. Yes, thank you.
Yeah.
All right, so from here, do we see any identities? Well, that's debatable. Yes and no. Not directly. Or if you're thinking, well, cosine squared, that's equal to 1 over secant squared, right? That's not going to get us anywhere, though. Okay? We could try, but that's not going to get us very far. What I'm looking at or thinking about is that sine squared plus cosine squared, that's equal to 1, isn't it? So, could I get cosine squared all by itself? Could I subtract the sine squared over? Like that? Again, on the left side, these are going to cancel. So is it true that cosine squared is equal to 1 minus sine squared? So if that's the case, what can I put in place for that cosine squared? Just a substitution problem. What can I put in its place? So I could rewrite this as sine x on the outside times, and you're saying that I could plug 1 minus sine squared, x in place, and the rest of it stays the same? Do we see how we just utilized that identity for the first time? Now what's going to happen inside of those parentheses? 1 minus 1, that's good, cancel out. Subtract that. So we're left with sine x on the outside, negative sine squared x on the inside. Now, this is the way that we've written negative sine squared. Again, there's sine squared x. If you had sine cubed x, you'd write it this way, or sine to the fourth x this way. What about sine x? What does that mean? That's to the first power, isn't it? So when I multiply these, what am I going to get? Negative sine cubed x. Okay? That's our final answer. That's as simplified as we can get. How do we know that that's as simplified as we can get? Well, we got down to one term. That's a pretty good indication. Also, well, like what else could we do? I guess technically we could rewrite that as like 1 over cosecant cubed x, but I would make the strong argument that that makes it less simplified. That would make it more complicated. All right? So, all right, so taking a look at the next problem then. Take a look here. Whoops. Dropped things all over the place. All right, so next problem. Again, we have another binomial. This time, what we're looking at, we have sine x plus cotangent x cosine x. So again, it's a binomial. We have a term plus another term. So what we said on the previous problem is that anytime you have a binomial or an addition subtraction problem, we want to look to factor something out. It's always a great place to start, but we can't say with any certainty that it's going to work 100% of the time. Like for instance, right now, nothing factors out. So one of the things that I've noticed over the years is that, and again, in no way is this mandatory or is this, the end-all, be-all way of approaching these problems. But one of the things that I've noticed is that, over the years, is that a lot of students kind of, I don't know, panic is the right word, but I'll say that they feel less comfortable with certain trig functions. I guess what I'm saying is that usually people feel okay with sine and cosine, and then they feel okay, kind of, sort of ish with tangent. But when it comes to the reciprocals, they oftentimes don't feel great about secants or cosecants or cotangents. So one of the tactics that we use, as simple as it may sound, is that we could just rewrite everything in terms of sine and cosine. So I could rewrite this, sine x plus, now instead of cotangent, I could write that for what it actually is. That's cosine x over sine x times my cosine x. Now again, at this point, in all sincerity, I don't really know if this is going to work or if this is going to get us anywhere. But I do know that sine x is over 1, cosine x, that's over 1. And when I multiply here, what that's going to give me is sine x, again, technically over 1, plus, when I multiply fractions, I just multiply straight across. Cosine x times cosine x is cosine squared x over sine x times 1 is sine x. Now, without making this harder than it needs to be, I'll be the first to admit, I understand completely and fully that this is trig, so it seems more complicated. But really what we have here is, what if we saw something like, I don't know, 3 over 1 plus 2 over 3. We're not going to be able to add these together until we get common denominators. How am I going to get common denominators, you might ask? Oh, we'd multiply by 3. The catch is, we multiply the denominator, we also have to multiply the numerator by 3. And pretty soon what we're actually doing is 9 over 3 plus 2 over 3. Common denominator of 3, adding my numerators, we would get 11. Now again, what does 11 thirds have to do with the problem to the left? Very little, other than the fact that we're actually going to mimic the same movements. I need to get common denominators, so I'm going to multiply by sine x. If I do that on the bottom, I have to do that on the top. So in the top, when I multiply sine x times sine x, I do get sine squared x over sine x. Over here, I still have my cosine squared x over sine x. And we've done it in the sense that we have common denominators, which puts me at sine squared x plus cosine squared x all over sine x. Remember that right there, sine squared plus cosine squared is just 1 over sine x, and 1 over sine is simply cosecant Yes.